Okay, good evening, ladies and gentlemen. So I welcome you all for today's Institute lecture. So we have a speaker, Dr. Jägle from Max Planck Institute for Iron Research, which is located at Düsseldorf in Germany. So now I request actually Professor Vivek Panchori to welcome our speaker.
Thank you.
So before we start, I would like to introduce the speaker. So Dr. Jägle has obtained his diploma in material science from University of Stuttgart, Germany, and then he moved to England for his MPhil, where he did his MPhil in materials modeling. And during that time, he worked with Professor Additive for modeling the banding in steels. Later on, he moved back to University of Stuttgart, and then he did his PhD at Max Planck Institute for Intelligent Systems with Professor Multimaterial. And the PhD work was related to mesoscopic simulations related to phase transformation kinetics. And after that, he moved to Max Planck Institute for Iron Research in Düsseldorf in the department of Professor Jägle. And there initially he spent time with atom probe tomography, especially with the materials like electrical steels and laminated materials to understand the mechanical engineering, mechanical alloying concepts. And now he heads a group in the same department, which is the alloys for additive manufacturing. So with this introduction, now I welcome Dr. Jägle to deliver his lecture.
Okay. Good afternoon, ladies and gentlemen. I'm very happy to be here. Thank you very much for the introduction, Sairam. I'm very glad to be here and at this prestigious institute. I arrived on Thursday, and so far I already had many very stimulating scientific discussions, and I'm really looking forward to continuing our collaboration, our scientific collaboration. Now, this afternoon I will be talking about a subject that is, well, my research subject is part of what I'm going to talk about, but this is not my research subject. I'm going to try to give you a little bit of broader overview over the topic of additive manufacturing and 3D printing and what that even means, and especially why there is at the moment so much interest, or one could even say hype about it. But before I dive into the subject itself, I have to give you at least a few glimpses about where I'm from, about the institute, where I'm working at. Then I will define what it is that we're talking about at all, what is additive manufacturing and what is a hype. And finally, as you can see, I will speak about when it makes sense to use additive manufacturing. What technologies are coming up at the moment beyond the state of the art, what the impact on society is of all of these technologies, and finally, as I wrote in the abstract, I will try to look into the crystal ball a little bit and talk about the potential future as I could imagine it in evolving. So first of all, I'm from a Max Planck Institute, not the Max Planck Institute, as many people often say, because there are more than 80 Max Planck Institutes throughout Germany and very few also abroad. And so you could say it's a group of institutes that all belong to the Max Planck Society. In the Max Planck Society, all institutes are doing fundamental research on all different topics, from ornithology to international law to empirical aesthetics to steel research. You can really pick a Max Planck Institute according to your interests, and here's the map where you can find them. This little dot here is our institute in Düsseldorf, in the extreme west of Germany. Now, one thing that could be interesting for you is that Out of the 14,000 scientists working at the various different Max Planck Institutes, 47% are not from Germany. And at my institute, actually, you will be hard pressed to find a PhD student from Germany, actually. And practically all Max Planck Institutes, English is the language of instruction and of daily life in the lab, I would say. Actually, even the PhD student who is accompanying me is not from Germany, he's Austrian. Yeah, right. Yeah, so we're at the Max Planck Institutes, we're quite proud that we have a long and prestigious history of many famous names like Albert Einstein, who worked in the Max Planck Institute. Back then, of course, it was known as the Emperor William Institutes in Berlin, and so on and so forth. Right, but the one institute where I'm from is a little bit the odd one out between the institutes. You can already see from its name, we are a limited company, and that is unusual for a research institute. And the reason for this is that we're a 100-year-old public-private partnership, you could say. Yeah, so the institute in Düsseldorf was founded really as the research lab for the German steel industry. And we have for many decades been financed 50% by the German steel makers. Nowadays, of course, this umbrella organization called VDEH it comprises European steel makers and includes, you know, ArcelorMittal and Tata Steel and so on as well. So in recent years, this part of our work has decreased a little bit, freeing us up also to work on other materials other than steel, which can also be fun. So you will even find people working on solar cells in our institute, and of course all different other metallic alloys. Right, so we're a relatively small institute. We only have 350 employees, including administration and technical staff. I would say for a steel institute we are relatively old, not quite as old as IIT Roorkee, but we're celebrating our first century this year. And there are 4 departments inside this institute. The department of Professor Neugebauer is working on computational materials design. So the guys who work with computers get the smallest building, obviously, yeah, because they don't need the lab space. The department of Professor Stratmann, or previously of Professor Stratmann, he recently became the president of the Max Planck Society, is concerned with interface chemistry and surface engineering, electrochemistry, corrosion, hybrid materials between polymers and metals, and so on. The department of Professor Dehm works on the structure and the micro and nanomechanics of materials. They do a lot of small-scale testing, in situ experiments in TEM, and so on. And finally, the department of Professor Rabe, where I'm located, is called Microstructure Physics and Alloy Design. Okay, so my group is just a small group comprising 6 people, including myself, and we started 2.5 years ago, roughly, was the unofficial start of the group, and we get our funding from various sources, as you will see, I think, in the very end. All right, so one more institution I have to introduce, and that is the National Academy of Science in Germany. Why do I need to do this? Because a lot of what I will tell you over the next 38 minutes is actually coming from what I learned at the working group Additive Manufacturing and 3D Printing. Now in Germany, the National Academy of Science is not as prominent as in other countries. I think, for example, if you go to France, the Académie Française is super important. In Germany, it is lesser known because the reason or what this academy is for is to give policy advice mostly. Yeah? So they're producing mostly white papers. Their members meet in various working groups, and then they produce white paper as guidance for politicians on what policy changes are necessary in the future based on hard scientific evidence. Hopefully they read it. So Professor Rabe is the chairman of this working group, but since I'm the organizer, I get to do most of the work, and I get to listen into, of course, all of the discussions. So what you will hear in the next minutes is based on the discussions between roughly 15 professors from medicine to mechanical engineering to social sciences and so on. All right, now when I want to tell you what's beyond the hype in additive manufacturing, first I have to tell you what additive manufacturing is, and then I have to tell you what the hype is. Now I hope not all of you have already attended either my plenary lecture at the AMPCO conference on Friday or the one-day workshop on additive manufacturing yesterday, because then you can switch off your brain for a few minutes right now. But for the rest of you, I will explain what additive manufacturing is. Okay, so additive manufacturing at its core is very simple. You build up a 3D part layer by layer. Yeah? And importantly, you start with a computer file. So CAD, computer-aided design, you start with such a file, and using typically a specialized software, you slice it into virtual layers. So from the bottom to the top, this volume data information gets turned into information that is already readable to the machine that will make it. These virtual layers you transform into physical layers, so you need a machine that actually does that, and thereby you build up your 3D part. So I always like to say all the magic happens inside of this arrow. So this is where the entire manufacturing process, the material science and so on, this is where all of this happens. So here is just one example of an additive manufacturing process called laser metal deposition. You can see how the laser is coming here. Coaxially there's metal powder being blown into the melt pool that is generated by the laser, and you rotate this structure here in the bottom, and therefore slowly you build up this conical structure here. All right, but even though of course I'm a metal specialist, as you can tell from my affiliation, these kind of processes where you can work with metals are by far not the only additive manufacturing processes. In fact, okay, before I come to the big variety, let me just give you the key features of additive manufacturing. I already said that a 3D part needs to be built up, so cladding is not allowed. This doesn't fit the definition. It is built layer by layer, and crucially without any specific tooling. This is what enables the quick build up of any creation that only 5 minutes ago you have thought up in your brain. In near net shape, yeah, in some processes nearer than in others, and again crucially in a computer controlled process. Yeah? So the full digital chain is really a hallmark of additive manufacturing. Right, now back to the slide that I wanted to talk about a minute ago. So this we have in additive manufacturing a very wide variety of processes. So whether you want to build up a part made up of living cells, or high temperature nickel-based superalloys, or throw away cheap as could be plastic, of course you will need a different process. And therefore a whole big range of processes exist, and this is not even comprehensive. I know you can't read all these processes, and I'm not going to go through the list of them, but just to give you a feeling that there are many different processes and many different machine vendors, of course, correspondingly, and those are applicable to many different materials. Yeah? I will here only focus on two processes. The first process is called material extrusion, you could call it. Specifically, the process inside this family of material extrusion processes is called fused deposition modeling. And this is what most people mean when they say a 3D printer. I bought a 3D printer and brought it home and I played with it. This is what people mean. Here you see the schematic. The material is supplied as a thin wire, typically called filament. These feed wheels push the wire into the heating element where it is molten. It's a thermoplastic material that can be molten, and then it is pushed through a thin nozzle and laid down. And this entire setup here moves in a computer controlled way. So let me show you, let me play you a small video from the University of Loughborough. Is it running? Yes, it is running. Good. So this is what the process looks like in reality. Here you have the nozzle. You can't see where the filament is coming. It is from somewhere here from the top. These bars are sort of what's giving the Cartesian robot its positioning. And now we are in fast forward mode, and you see how this platform is slowly lowered as layer by layer this entire model of a race car is built up. Okay, and now we're back to real speed. All right, already here you see some tedious post-processing actually. That is also unfortunately quite typical of additive manufacturing processes. So if you go to amazon.de and type in a 3D printer, basically the first 5 pages that you will see all work according to this principle. Yeah? And if you, so the cheap ones here cost 250 to 300 euro. If you go to aliexpress.com, you can find them even cheaper. You can find 3D printers already starting from $150 US dollars, although I wouldn't count on these guys working straight out of the box, to be honest. But it is a very nice tool, even for people working professionally with additive manufacturing with much more expensive machines, to get used to the concepts that are surprisingly well translatable from one process to the other. Now, selective laser melting is the second process that I want to show you in a bit more detail, and this is the process that we use in the lab to make metallic parts. So you spread a very thin layer of metal powder, typically 30 to 50 micrometer in height. You spread it on a substrate or on your already existing part, and you use a laser to generate a melt pool locally where you want to melt it. Yeah? So this laser beam is scanned using movable mirrors across the powder layer, and thereby you build up your part. Of course, you repeat again a new layer and so on. And you can see this here in this little movie. One powder layer is spread on the platform, the laser comes in, up here is the scanner that moves this laser beam, and only where the laser beam, this is now the real process, actually the spreading quality is not very good for this layer, and wherever the laser hits, the material is molten, and when it moves away it resolidifies and leaves a solid part. Now this process gets repeated. Here is just schematically over and over and over. You would repeat this layer by layer build-up, and then you can realize these very complex parts. Now I brought you another video, and here you see how this process works, not in a schematic but in real time and at high speed. And you see that it's a very dynamic process. You see here how the powder particles get kind of sucked by the convection of the gas, hot gas that is rising above the melt pool. They're sucked in and they follow the laser beam, and nevertheless, you know, most of them get molten and most of them get deposited. But this video I just copied in here to show you that we're talking about a very dynamic process. And when I see this video, I'm always amazed that we get dense materials out of this process at all. And this also shows you that this is not a very, you know, clean and perfectly controlled and stable process. This requires more work from engineering and from mechanical engineering, from material science to make it more robust. Nevertheless, it works well. It has been in development for, I would say, 20 years. And we are now ready to bring this, we're not ready to bring it to market, it already is in the market. Yeah? And this is what I will show you. So, the hype of additive manufacturing. What do people mean when they talk about hype? Well, there is this one consultancy company who tries to define what a hype is, and they have come up with the so-called hype cycle. They publish it yearly, and they just say, okay, the visibility of a given topic as a function of time, and okay, at first nobody knows about it, and then you were here at the so-called peak of inflated expectations, and this is where the most of the hype is at, where everybody's talking about it and thinks that this can take over the world, this technology, but as more and more people are actually using it and are making their first experience with it, they fall down into the trough of disillusionment when they realize that no, the world is not going to be changed and Rome wasn't built in a day, and actually the paradise is not coming because of this new technology. But finally, along the slope of enlightenment, when they first of all use the technology better and use it for the purposes where it is best used for, then we reach the plateau of productivity where the technology is fully established. Now let's have a look at the hype cycle that they published in, before we look at the hype cycle, I just copied in a few recent headlines from various websites. And if you read this, you would think that we are really on the peak of inflated expectation, right? 3D printing will change the world radically, and it's an industrial revolution, although it's not very clear whether it's the third or the fourth industrial revolution, but certainly it's an industrial revolution. And so when we now look at the hype cycle, you would expect 3D printing to be at the very top, right, of the peak. It's actually not there. So in 2015, 2 years ago, summer 2015 that was published, consumer 3D printing was already falling down towards the trough of disillusionment, and enterprise 3D printing was rapidly ascending the, the slope of enlightenment, right? And what about 2017? What about today? Well, it's not to be found. We find 4D printing, and I will talk about that later, but we don't find 3D printing at all anymore. Why? Because it has become its own category, and it is not in the so-called emerging technologies hype cycle at all anymore for this specific consultancy company. It is already well established. Yeah? So according to these here, 3D printing is not in the hype at all anymore. Here you see the individual hype cycle for 3D printing, and there you see that there's a huge variety again of different processes, of different applications, and they fall all the way from absolutely new nanoscale 3D printing, 4D printing, to absolutely well established, such as 3D printing for prototyping and 3D printing of hearing devices. All right. Now, the market size that is current and that is projected is quite interesting. So it is growing, of course, pretty rapidly, but then when you realize that this figure, this figure here and this figure here for 2018 and 20 are of course projections, and if you actually, look at this slope here, even assuming it's an exponential, people are still waiting for the breakthrough of this market size, yeah? And right now, with roughly €5 billion market size globally for all 3D printing, machine making, services, raw material, that is actually still a tiny market worldwide. Yeah. However, very large expectations. Yeah, expectations of very rapid growth in the future. All right. So we've seen that on the one hand, people have high expectations. On the other hand, they're already through the trough of disillusionment and are already climbing up the slope of enlightenment. Now, what do these enlightened people use additive manufacturing for? What is it good for? For example, the hearing aids. Yeah, that was already in the hype cycle on the far right-hand side, close to the plateau of productivity. We have AM of hearing aids, and this is what they mean. Yeah, so people are getting older and older. They need hearing aid as they turn older, or some people already, unfortunately, when they're younger. And all of our ears are shaped differently. So we all need, ideally, individually produced hearing aids. And additive manufacturing is perfect because you can produce without effort for every person their own individualized hearing aid, and you don't need a person sitting there who will, carve it out of some material and fit it to a person. In in a country like Germany where labor is extremely expensive but technology is comparatively cheap, this is of course a big advantage, and the hearing aid industry in the US and in Europe has practically completely shifted already to stereolithography, a different additive manufacturing process, to make these parts here. Yeah? So here we are already absolutely on the plateau of productivity. Okay, what else? How can we know when additive manufacturing would be useful? Whenever these three requirements are given in a certain industry. First of all, what people sometimes call individualization for free. If you produce few parts of the same shape, then it is much better to use such a process that is toolless and near-net shape rather than other processes. Yeah? So here you have a big cost advantage. By the way, here on the axis is always cost per part, and in this case it's lot size. Now here, what people call complexity for free, you have of course the product complexity on the axis, and the more complex a part gets, the more difficult it becomes to produce it, for example, with milling. So again, additive manufacturing has a big advantage. Finally, weight reduction for free. This is very much connected to this complexity for free. The more complex a part gets, the more, the less material you actually use, because there's a lot of holes and the struts are very thin and so on, the better actually for additive manufacturing. So you're even getting cheaper. The less material you use, the more weight you reduce, for example, in an aerospace part. And of course, if you mill material away, the more you mill away, the more expensive it becomes and the more scrap you're producing in subtractive manufacturing, for example. So this gives you already a guideline. Now let me give you some examples. Yeah? First example, using this, what do they call it, individualization for free. Manufacturing of the few. Yeah, you can. What is now possible is a business like Shapeways, where you can go to their website, you upload your CAD file, click print, put in your credit card information, and 2 days later you receive an individually made part for you. Yeah. So what also people sometimes call tapping into the long tail of the demand distribution. This is possible with additive manufacturing. What for industry is very, very interesting as well, apparently, is to make spare parts on demand. At the airport in Frankfurt, just before I was boarding my plane to Delhi, I saw this advertisement. When 3D printing is commonplace, will we still need warehouses? Yeah? So this is exactly what I've been talking about with the spare parts on demand. Yeah? You don't keep the spare part somewhere. Whenever you need it, you make a one-off piece. And the ultimate one-off piece are already prototypes. Yeah? So this technology in prototyping is also absolutely state-of-the-art, obviously. Okay. Next use case, when you exploit the complexity for free. For example, you want to make a die for a plastic injection molding, and instead of making the cooling channels by deep hole drilling that don't allow you to go close to the contour here in this rounded edge, you just print them in. You print your entire tool out of AM, and then you can have complete freedom of where you put the cooling channels, and you increase the productivity tremendously. Also here in these examples, this one in particular I will show on the next slide. So this is very interesting in aerospace and in tooling, and therefore, of course, the materials that are used here are also light materials as aluminium and titanium and tool steels and so on. Now, sorry, let me skip to this one first. Here, this is the part that I showed on the previous slide. So this is a fuel injector for a GE plane turbine that is going to be, or that is, I think, already flying in the Airbus 320 Neo new engine option aircraft. And there they used another advantage. Instead of manufacturing 20 different parts, as they had done on the previous design, they print this out as one part, as one monolithic part, with all the complexity that you need for this fuel injector already printed into the part. And this not only leads to a weight reduction, because they can get rid of the joining and the fasteners and so on, it also increases the lifetime apparently. And they will need projected need for these injectors are 40,000 per year. So that's already quite a number. Not if you come from, I don't know, the injection molding industry, or if you come from any automotive supplier, then 40,000 is of course, you know, 2 days worth of production. But for the aerospace industry, for high value parts, this is already quite something. Okay, here are more examples of the complexity advantage. You are able to replace something milled like this, something printed like that. You can go crazy and make fully electric motorbikes, for example. You can replace the inside of every part with lattice structures like this. And here I just want to highlight the need for a software that can do this and that can deal with it, that can do this topology optimization and that can work with these lattice structures easily. And secondly, the need that design engineers, of course, need to learn about these techniques in order to design parts that take advantage of it. Okay, let's move on to the customization. So this individualization for free again. Of course, as you already knew from the hearing aids, biomedical is the prime application where this plays a role. So not only the hearing aids are 3D printed, also the dental implants this is rapidly becoming state of the art, and other orthopedic implants as well. The attractive feature for these orthopedic implants is the porous surface. So depending on the process, you can deliberately make the surface very porous, and this helps in osseointegration, so bone ingrowth into the implant that you're getting. Now this picture here actually my wife has taken in the University Hospital of Düsseldorf. Not quite as fancy an application as this one, but very important nevertheless. So she snapped this picture somewhere in an operation room for brain surgeons, where they apparently had to make a very complex surgery where they were entering the brain cavity through here I don't know what the proper name for it is, but basically through the eye socket. And as you can imagine, this is a rather complex surgery, and to make sure that they don't screw it up at all, they did a CT scan of the patient's head, and then they 3D printed it and already tried out how to do the surgery beforehand on this model here. So again, very interesting and useful application of 3D printing, and again, already not the future but the present. Okay, and finally, just because I like looking at these pictures, the so-called artisan products, so products that are highly customized, very complex and low volume. These products you can also print, and that is, for example, jewelry. Yeah? So there is a certain market for additive manufacturing machines specifically for noble metals. So if you want to give a very unique wedding ring or engagement ring, then next time go for additive manufacturing. Okay, so this is the state of the art. Yeah? I've already shown you that when you pick the right application, then we're actually already on the plateau of productivity or reaching it very soon. Now, what's next? What is still somewhere around the peak of the hype cycle? Those are what I labeled here emerging AM technologies. Those will not be connected on each slide. I will just give you one glimpse and 2 sentences of these very different aspects. So, additive manufacturing has a multi-scale problem in the sense that if you look at, I don't know, for example, your laptop, you need parts that are very different in size. For example, the case is rather large, and then you have the tiniest screws and so on and so forth. And if you have an AM technology that can produce very fine parts, it will take ages to produce a large part, right? And vice versa, if you have an AM technology that produces a large part, it will not have the geometrical resolution to produce a very fine part. So in order to solve such multi-scale problems, people propose, for example, 3D printing a part, but leaving a cavity. In this case, it's for an RFID chip that you can put in and then resume the printing process and have a smart insert fully embedded in, I think in this case it's a tool or something. Yeah? So this this makes your product smart, and this solves the multi-scale problem. Another one is actually, in many cases, you will need limited machining post-processing of these parts, which is why it's a near net shape operation and not a completely net shape operation. And therefore, when you have to, let's say, do a little bit of machining afterwards anyway, it makes sense to combine additive and subtractive into one machine. That is actually something that we will see a lot in the future, where the 5-axis mills that are completely computer controlled, as one additional tool, you will see them having also a deposition head. So in the combination of additive and subtractive, ideally you get best of both worlds. Sorry for the typo. Okay, AM does not only have a multi-scale problem, it also has a multi-material problem. Here actually I've given you the examples of multi-material 3D printing that already work. So you can print in full color, yay. You can also combine flexible rubbery type polymers with hard polymers, or transparent and non-transparent polymers. So there it already works. In the metal world, combining different materials with the powder bed processes is absolutely not to be seen at the moment. So this is a problem, but at least we can look forward to something like this, where you combine polymer 3D printing together with integration of electronics and printing of the required connectors there. Okay, well now this is a topic that is of course very close to my heart because it's my own research subject, materials for additive manufacturing. Until now, the materials that are in use in AM are off-the-shelf materials that have been initially designed with other manufacturing processes in mind. Casting, forging, rolling, whatever. And if we want to exploit the full potential of AM, we will need to design materials that are suited to this process. Yeah? So the material development and the process development will need to go hand in hand. I just copied two quick examples for if you use processing with flow cooling rates. In this particular case of aluminium scandium alloys, you can only put in 0.1 weight% or 0.2 weight% of scandium, otherwise you will not keep it in solution. However, when you use additive manufacturing and have access to rapid cooling rates, high cooling rates, then you can put in 0.7 weight%, and the number density of strengthening precipitates increases by a huge number, and therefore your properties also become better. So this is one example of a material that only works in AM and not in conventional manufacturing. And here, I don't know if you want to call this a material, often it's called an architectured material or a metamaterial. You can build these foams, these lattice structures in a certain way, such that the overall material behavior is a negative Poisson ratio. Yeah, so as you compress it, it also, perpendicular to the compression axis, it also compresses. There's also acoustic metamaterials that have interesting sort of negative indices of refraction and so on. There's interesting metamaterials for RF applications, and all of these can be produced easily by 3D printing, and you would be very hard pressed to make them otherwise. Okay, now this is something that friends send me regularly on Facebook, and they say, hey, you work in additive manufacturing, right? Look, now you can also print your pancakes with additive manufacturing. It is true, you can buy these machines. I have no idea why you would want to spend 500 euro on such a machine to make a shaped pancake, but well, you can also, make shaped gummy bears. You can buy chocolate 3D printers. So this is of course absolutely a novelty item. Yeah, I mean, if people will buy it, I'm all for it. Yeah, but I don't think it's going to change the world. However, there are also certain let's say earnest uses for food 3D printing. So that was a research project funded by the EU, where people have ground food to make it eatable for people who cannot swallow easily. You have a damaged sorry, now again I'm missing the English word, but you know what I mean. If you cannot swallow properly, maybe you know from the last time when you had a cold, and some people, often elderly people, have this problem permanently. So the food gets ground and then 3D printed again in a shape that looks like the food that they're used to. Because these people often stop eating altogether, because you know, when you have to eat mash all day long, that will get very boring at some point. And therefore this apparently really helps them to stay healthy. You can also add nutrients as well. So there are even good uses for food 3D printing. 3D printing in architecture is also a topic of research, current research. And here are 3D printed houses in Dubai. This is not a computer simulation. They really claim that they look like that. I don't know, I haven't been there, but here is a 3D printed bridge that was made in the Netherlands, sort of by kind of a welding deposition. And here is the vision of what I think a company in California envisions this. Now, I'm a little bit skeptical. So in any case, this needs to be hybrid manufacturing. Even here you see that the 3D printer does the walls, and then here the roof is just being picked and put in place. Yeah? And a house is much more than its walls. Yeah? It's electrical insulation, it's piping, and so on and so forth. And if all of that stays manual, then how much do you really gain by making a couple of bricklayers unemployed? I'm not sure, to be honest. Personally, I'm not convinced that this is the future. However, possibly, some people have suggested that this could help in very quickly building houses after a disaster, to speed up the process a lot. And some people, and there are examples of these 3D printed houses. Again, by the way, a multi-material problem. If you have a printer that can print pipes and print electrical lines and walls, then you're much closer to your goal, I would say. 4D printer, this is one of the technologies that you already saw in the emerging technologies hype cycle. So what is 4D printing? You have 3D printing, and on top of that, as fourth dimension, you have time. So you print something out, and due to the behavior of the material, after you print it out, it will on its own self-assemble in a certain fashion. Yeah, so maybe you soak it in water, or maybe you heat it up. Maybe it's a shape memory alloy, maybe it's a polymer that stretches when it takes up humidity. Anything like that you can use to print a structure such that it is pre-programmed to form later a different structure. So again, I'm not sure what the applications of that will be, but it's definitely an interesting concept to toy around with, I would say. So 4D printing. And then another upcoming topic is high-speed printing, both for polymers and for metals. Why is that important? Well, you already saw earlier the video of fused deposition modeling needed to be sped up because this takes time. Yeah? I've wasted far too many hours sitting in front of a 3D printer looking at it mesmerized. But the fact that I wasted hours and not minutes already tells you that all of this is slow. Yeah? Again, this is why mass production is not going to work well with AM. So there's a lot of work in speeding up additive manufacturing. For example, polymer 3D printing. So here, the build platform is put down into a vat filled with a resin. And what you don't see is where the actual innovation of this company is happening, and that is here at the bottom of this vat. There is a window, and they're controlling the oxygen permeability of this window such that the material does not stick to the window. Normally, when you build the layer, the material always sticks both to the substrate platform and to the window, and then you have to sort of wipe it away once, maybe by tilting the platform, and then you can build the next layer. Here it doesn't stick, so you can polymerize the entire layer at a time, and immediately after it is polymerized, you lift it up and you do the next layer, and this speeds up the process a lot. So even though, you know, this is also sped up 7 times, overall I think the video was a minute, and therefore this entire little ball was printed in just 7 minutes. I would say with a conventional FDM 3D printer that would have taken 40 minutes or something like that. Yeah? So this is a tremendous advantage. Also in metal 3D printing, people are not only looking at SLM but also at other processes. So there's one company in the US backed by various MIT professors that is called Desktop Metal, and what they do is so-called binder jetting 3D printing, and then debinding and sintering. So this process shares a lot of its process chain with metal injection molding. Yeah, so it's exactly from the materials science point of view, it's the same as metal injection molding. You just replace the actual injection molding as a shaping tool of this binder and metal powder mixture, and you replace it with a 3D printing process. So here is the video where you see how this works. I would like to forward a little bit, but I don't see. I think here I can forward a little bit. Okay, so this is their machine. And here you see a powder bed. This is the powder bed with a metal powder. And two print heads are going back and forth. First, the metal powder is deposited, it's forming a thin layer. The powder is compacted. And then the actual binder is selectively deposited with a print head that is very simple, very similar to an inkjet 2D printer, paper printer. And then the printer needs to be, the binder needs to be dried, and then you repeat this over and over again. Okay, and finally you sinter it, and what they claim is that using this method the productivity is much higher, and instead of the 12 parts that you can make with the SLM per day, they claim, obviously inflated marketing numbers, you can make 560 parts per day. Okay, so speeding up the process, if this works and if this establishes itself, it's definitely going to change metal 3D printing quite a bit. Bioprinting, yeah, this is of course a very big topic. Yeah. So this is what you want, a machine, you press a button and a new liver comes out, and that is the reality. So some don't believe the companies who say that next year they will print a liver. Right now we're at the stage where cartilage can be printed out, and where maybe the outside of an ear can be printed, or new skin can be printed. Big achievements, yeah. I don't want you to underestimate it, but we're nowhere close to printing a full a functioning organ. Again, the multimaterial problem and the multiscale problem are there. Okay, I'm running a bit late, so I will keep the societal impact very short, but just give you a few keywords to think about in the next slide. So home 3D printing is here. Here you see my PhD student, Priyanshu, with a 3D printer that we use for outreach activities at my institute. This is my workplace at home, where I have my own 3D printer to play with. The printers are now in a price range where they are affordable, especially if you buy a DIY kit. Now, will every family have a 3D printer in their home eventually? I'm not so sure. The key question is, of course, will they get value out of it? Or will it be like your paper printer, where you curse at it every other day because it eats up your paper and produces jams? Yeah? And I can tell you the DIY printers produce a lot of jams at the moment. Yeah? They're nowhere near press and play. So again, I have the feeling that maybe the home 3D printers will stay confined to the maker community and to some subset of the population who just like to play with these things. Yeah? Toys for grown-ups. However, I think it will establish itself as a product category. It's not going to go away completely. The future of work, yeah. So in Germany particularly, we're always discussing whether robots will steal our jobs, right? And you know, maybe they will, but I don't think additive manufacturing is going to contribute very significantly to that. Because right at the moment, AM requires a lot of manual pre- and post-processing. The manufacturers of the machines are working very hard to stop this. They're trying to automate the processes as much as possible. However, right now AM is even creating more jobs, highly qualified jobs, however, and in the future one can easily envision that an AM factory is almost completely without human interaction. There's one designer pressing the button and the rest is more or less done automatically. So the vision is not completely to be dismissed. This I just have thrown in because it's a nice example where 3D printing might help in the preservation of artifacts by 3D scanning, and then reproduction can be used in teaching and so on. I will move on quickly. Now, additive manufacturing is a fully digital process chain, right? Even in the definition I gave, it needs to be digital. And since it is completely digital, a lot of the know-how of how to make this is not in the head of the machine operator, it can be embodied in the process parameters. And since it is in the process parameters, and since this is fully digital, it can be shared easily by email, and what can be shared can be copied and can be stolen. So there was in the US, this was an anti-music piracy advertisement in the 1990s, apparently, no, in the 2000s. And they always said you wouldn't steal a car, and the joke is with additive manufacturing you can actually steal a car by stealing the blueprints and the manufacturing recipe for the car. So this is definitely something people are worried about, yeah? And the anti-piracy efforts are a big part of what is going on in industry with AM at the moment. Right, for 2 years ago there was a big scare about 3D printed pistols, and it was a huge outcry in the media and the uninformed media. Do we need to regulate 3D printing? Is it dangerous? And of course that is stupid, because even this gun here that can barely fire 2 bullets before it explodes in the hands of the person who holds it has metal parts for its most important bits. So I would say I would completely dismiss the security issues of AM, because if you can afford a €500,000 3D metal additive manufacturing machine, with which of course you could make a weapon, then you can also just afford a simple lathe and build the gun barrel with that, and probably get a much better result. Okay, I don't want to stop talking without mentioning in the environment. It is often claimed that AM is very environmentally friendly because you only use the powder that you need and recycle all the rest. And moreover, you make very light parts, and therefore over the life cycle of this part it will help save fuel, for example, in an airplane. This is all true. However, it is not trivial to know whether a part will be over the entire life cycle, including recycling and so on, and including, crucially, making the feedstock of the 3D printing process, will be greener than the conventional counterpart. It could be, and there are case studies that show that it is, but in other case studies they also show that it is not. Yeah? So if the goal is to become greener, we really need to make the life cycle analysis, and 3D printing is not a no-brainer. We're dealing with polymer powders. We know that microplastics is a pollutant that is so far underestimated. So this we need to keep in mind, and we also need to keep in mind that health and safety hazards do exist during the industrial additive manufacturing, however, not more than you have in other powder metallurgical processes. And with that, I'm at the end. So after listening to all of this, do I say that additive manufacturing is going to change the world? Is it overhyped, or is the hype actually good? I would say it's not going to rapidly change the world, but it is here to stay. So in industry, it has already established itself as one more production process in the large variety of processes that are there. In some specific industries, it is going to completely replace the existing manufacturing routes. In others, it is going to become a part of the manufacturing routes. It is most probably not going to change our daily lives, but also here in the home, maybe it will enter the home of many people. Maybe it will another thing that we can use to make small repairs at home, and also there it is here to stay. So with this, I would like to thank my group who does all the research together with me, and I would like you very much for your attention.